Hi everyone, I'm Leonardo Bonatti. I'm a PhD student at the Institute for the Wireless Internet of Things at Northeastern University, and I'm going to talk to you about Scope, an open and softwarized prototyping platform for NextG systems. So NextG cellular networks will be based on an Open RAN architecture where the performance of the RAN can be optimized through third-party applications. While this brings high promises, it also brings some specific needs. For instance, we have the need for open research tools to prototype such solutions in a controlled environment, the need of large-scale datasets to design and train such machine learning and artificial intelligence solutions, and the need for open APIs to interface our control solutions with the white box architecture of an Open RAN. So as of today, this is not implemented. And we make a step forward in this direction to design Scope. Scope implements base stations and user equipments by extending SRS RAN with some 5G specific functionalities. It also provides automatic tools for the data collection of RAN statistics and flexible control APIs. So custom applications and control logic can be seamlessly interfaced with the cellular RAN at real time. We implement Scope in a portable way through LXC containers, and overall Scope enables the prototyping of custom control logic at scale on cellular networks. So as an example of Scope APIs, we can use them to control the RAN by simply inputting few high-level directives. So as an example, we have that we first load the current network performance at runtime. And then for each of the network slices, we get the slices of the users of that slice. We get the resources of that slice. We set custom parameters such as the modulation encoding scheme for selected users. And if certain conditions apply, we reconfigure the RAN. So for instance, we change the scheduling policy from a proportional fairness to a round-robin scheduling algorithm. And this process can be iterated until some final goal of the network has been reached, for instance. We implemented Scope on Colosseum, which is the world's largest network emulator. And Colosseum allows users to virtualize containers on a white box infrastructure. Colosseum also has hardware in the loop with 256 USRP X310 software-defined radios, and it allows to emulate realistic radio frequency and traffic scenarios among its software-defined radios. Overall, users can emulate more than 65,000 RF channels between radios, and the goal of Colosseum is to allow the large-scale emulation of different scenarios, both radio frequency and traffic scenarios, and to evaluate softwarized solutions in a controlled environment. So if we use Scope with a testbed like Colosseum, for instance, we can emulate a custom scenario. In this case, we consider our own emulation scenario. And in this scenario, there are certain base stations and users deployed. So for instance, the blue circles that you see in the picture are the cellular base stations. Then this scenario can be used to evaluate the network performance. So for instance, here, there's an example on how the downlink throughput can be evaluated in these specific scenarios. And we can see that when some unforeseen event happens. So for instance, a new group of tourists arrives in the emulation scenario, we have a degradation of the network performance. So if we were to do this without Colosseum, this wouldn't be so easy, as first of all, we would need to travel on site. So in this case, we're considering Rome, Italy, so we would need to actually get there. We would need to ask cellular operators if we can use their actual commercial infrastructure, so the very same infrastructure they're using to provide a service to their customers. with the result that with all the risks involved in testing, possibly not stable and not production-ready solutions on a real infrastructure, the operators would say no. So your experimental campaign wouldn't simply happen. So scope allows to prototype solutions at scale, and here there's an example on how scope integration works with Colosseum. So we provide a plain scope container that every user can instantiate seamlessly on the testbed, and this container can be customized to add some custom user control logic. So for instance, the first step would be to get this plain instance of scope and implementing some custom control logic, for instance, optimization, control algorithm, or machine learning and artificial intelligence routines to optimize the run. So the next step would be to select a radio frequency scenario and a traffic scenario to run from the list of scenarios of Colosseum. And this would actually allow you to emulate a specific wireless environment and to evaluate your solution in a set of realistic configurations at scale. So the next step would be to interface the custom logic with scope APIs that are directly tied to the Cellular run, and in this way, the custom solution will be able to reconfigure dynamically the run based on the actual runtime performance. And as a plus, all the metrics of the run are saved at runtime, and they are available both for offline processing, so for instance, offline training or of machine learning and artificial intelligence solutions, or for instance, for online closed control loops. So you can access such metrics both at runtime and offline for training or post-processing and evaluation. This feature can also be used to create some large-scale data sets from your solution. So we talked about scope Cellular scenarios. So let me give you just an overview of what they are and what they can achieve. So these kind of scenarios allow you to specify various wireless conditions, so effects of the wireless channel, such as path loss, fading. Then we have the position of the users and positions of the base stations on a map. So for instance, for the scenarios that we've seen earlier on, we use OpenCell ID database to derive the realistic positions of the base stations on the map from real deployments. And you can also specify the mobility of the users, the speed of the users, or other factors. Along with RF scenarios, we can specify traffic scenarios. These are composed by different traffic types that we can have among nodes, and with factors such as type of traffic, priority, and data rate, and so on and so forth. And of course, we can also specify the traffic flows among each pair of users or base stations and users. And as an example, we designed some large-scale scenarios for scope, and we design a Rome, Italy scenario. We design a Boston scenario, and we design a Salt Lake City scenario, which actually mirrors the deployment of the powder testbed in Salt Lake City. How do these scenarios behave, though? So these large-scale scenarios are implemented with 10 base stations each and 40 users. And they're both static, meaning that there's no mobility involved, and dynamic, where the users move around according to such some mobility pattern. And we can see from this plot that we have a certain repeatability across multiple realizations of the experiment. So for instance, here we have 60 repetitions of each experiment. and we have a pretty good confidence of the results. So as another example, scope can be used to implement an adaptive run control algorithm. So the first step would be to design such machine learning algorithm to interface that with scope and with scope APIs to control the run at runtime, to generate the performance data set from multiple experiments using scope, and to train and test your solutions in different RF traffic scenarios and environment, and then to fine-tune the outcome of the custom control logic until the desired behavior is reached, and then to deploy such solutions on real networks. As an example of how scope can be used to implement an adaptive control of the Softwarized run, in this case, we monitor the downlink buffer from the base station to the users for various network slices. And we see that at a certain point, the downlink buffer heavily increases. And with the buffer, we also have an increase of latency. At this point, we change the run configuration of these slices. And in details, we double the resources of these slices. And we change the scheduling algorithm from a round robin to a proportional fairness algorithm. And we have a decrease in latency for these slices, but also an increase in the throughput of these slices by using this Softwarized control through scope. As another example, scope can be used to optimize Softwarized run by connecting it with the ORAN architecture. So for starters, we implement the Softwarized base stations on Colosseum with scope. And then we interface scope with the ORAN architecture and implement a closed loop control from the ORAN XApps to the actual base stations that are controlled through scope APIs. Also, scope can be ported to different testbeds. So we, for instance, first prototype scope on the Colosseum testbed, and then we validated our solutions on a real environment, such as the Arena testbed at Northeastern University. And then we tested the prototype solution on large-scale platforms of the Power program. And the result is that although these testbeds are very different among them, their performance is somewhat consistent to one another. And overall, scope facilitates the design, prototyping, and testbed of NextG solutions at scale and in a controlled environment. It also provides modules for automatically generating network performance and data sets that can be both used in an online manner to implement closed control loops between the customized solutions and the run. And this can also be used as an offline reference to train, test, and evaluate solutions and algorithms offline. And scope is open source and is flexible to any extensions. As said, we provide a set of predefined scope APIs that can be used to swiftly interface customized solutions with the run in real time and to reconfigure the run at real time. But additional APIs can be implemented to achieve different behaviors and objectives. And the scope implementation itself can be also modified flexibly to include other use cases or scenarios. And overall, scope is a portable implementation that can run on any LXC-enabled testbed, and this allows to first prototype solutions in a controlled environment at scale, and then to test these same solutions in real cellular networks. And thank you for your attention.